So for this lesson, we are going to put on our astronomy hats. Except that this isn't an astronomy class, so I'll do my best to stick to the most important points. Generally speaking, astronomers are agreed that the most likely origin of the solar system is a progression from space dust called a nebula, which eventually comes together because of that rascally force gravity. One space particle at a time they come together until the force is stronger and forms the solid Earth. If you have ever been interested in our local solar system, I'd recommend reading the text on your own, but this is an Earth history class, so we'll just skip to the Archean Eon. The process of all this space stuff coming together is called accretion. Eventually, the layers of the Earth discussed in the last video become differentiated, but the surface was mostly an unlivable magma wasteland. Additionally, there is almost no oxygen in the atmosphere at all. Oxygen didn't form until the beginning of the Proterozoic. The two processes that formed oxygen is called photochemical dissociation, or the breaking up of water molecules into their atomic pieces of hydrogen and oxygen, and then the more familiar photosynthesis, which is when plants take up carbon, water, and sunlight to make food and excrete oxygen as a side product. Remember when we discussed how exposure to oxygen results in a red colorization of the sediments? Well, the fact that none of the rocks from this time are red in their appearance, well, that's one of the clues that historical geologists use to determine that the early Earth atmosphere was not dominated by oxygen. Features called banded iron formations also provide evidence for the interaction between iron-rich minerals and the early Earth's oxygen. Where did the oceans come from? Well, all it took was for the early Earth to cool enough for it to start falling as rain, just like today. The chemistry of this early water is not like it is today, because the extra carbon dioxide in the early atmosphere would have made the water acidic until other processes introduced minerals to balance out that acidity. That explains how rain filled the low-lying areas of the Archean. But still is the question of where it came from. Essentially, these water molecules were likely trapped within that accreting space stuff discussed earlier, until it was squeezed out onto the surface to begin the process of evaporation, rain, and then more. Let's get specific about the Archean. It lasted from 4.0 to 2.5 billion years ago. These dates are calculated using the radiometric dating techniques that we've practiced in our labs. To find rocks as old as the Archean, you can visit the Canadian Shield, which spans across the northern latitudes of North America and totals to 7.75 million square kilometers of rock. Also, anywhere yellow on the map shows other places that Archean rocks are peeking out onto the surface. The first evidence for the creation of soils can be found in Australia, and it dates to 3.8 billion years old. Our best efforts to figure out the geography of the first continental crust has led to smaller and steep-sided landmasses that do not feature the continental shelf features that we learned about last week. These probably were around from 3 to 2.5 billion years ago. From careful study of 3.8 billion year old rock series from Greenland reveals evidence of the same kind of tectonic forces and resulting volcanic activity that is remarkably similar to the ongoing process at the mid-Atlantic Ocean. This means that only 760 million years after the Earth formed did the modern tectonic process kick into gear for the first time. After getting lost in the textbook's description of the major rock types of the Archean, the origin of Earth life is discussed. Modern biology informs us that the basic components of a living organism are in the DNA, which it itself is made of a collection of protein molecules. The question is, when did these biomolecules come together to form the DNA of the first living organisms? Well, unfortunately, this development of life is not directly preserved in the fossil record. Still, historical geologists are crucial to the investigation because we can determine the atmospheric and terrestrial conditions of the ancient Earth. This information was used in the 1950s to recreate those planetary conditions in a laboratory. This dude named Stanley Miller, in true mad scientist fashion, shot it up with a bunch of electricity. And in this controlled environment, the crucial biomolecules were created as a result of the introduced electricity, just like lightning introduced electricity into the early Earth atmosphere. But the atmosphere didn't have the things that plants need to make food, which is sunlight. The first organisms did not make food with photosynthesis, but instead with chemosynthesis. For our sake, we won't worry about the biochemistry of all this, other than that instead of using the sun, chemosynthesis relies on things like ammonia and hydrogen sulfide to process into the food. These chemicals are harsh and probably toxic for our type of life, but similar organisms that survived the harsh environment of the Archean can be found today in Yellowstone National Park. All that volcanic activity there heats up the underground water, which dissolves all kinds of nasty stuff into the water that would make it dangerous for us, but just fine for the same kind of chemotrophic organisms of the Archean. Since this is not a biology class, we do not need to burden ourselves with the biochemical pathways for food production in autotrophs, heterotrophs, chemotrophs, prokaryotes, and eukaryotes. Instead, the study of the rock does reveal that the earliest fossilized form of life are things called stromatolites. By itself, stromatolites are just another sedimentary feature. However, modern stromatolites have layers of organic matter in them, so the identification of ancient stromatolites does indicate life, even if the organic matter is long since decayed. And that about brings us to the end of the Archean Eon, so thanks for listening.